What's all the fuss about? Hello, science fans. Bill Nye here. Today we are diving headfirst into a truly fascinating subject. It is called artificial intelligence, or AI for short. You have probably heard these two letters buzzing around a lot lately. Perhaps you have seen AI in action in science fiction films, making robots think and talk. Or maybe, just maybe, you are using it every single day without even realizing it. AI is all about making our computers, our machines, think a little bit more like us humans. It is about teaching them to learn from experience, to recognize patterns, to solve tricky problems, and sometimes even to make decisions. Isn't that something? Science is truly all around us, and AI is rapidly becoming a massive part of our modern world. So what does it mean for a machine to think? Well, it is not quite like how you and I think, with feelings and daydreams, not yet anyway. For machines, thinking involves processing enormous amounts of information. They look for patterns and connections within that data. Imagine trying to sort 1 billion photographs to find all the ones with a red bicycle. That would take a human a very long time, wouldn't it? But an AI can be trained to do this task incredibly quickly and accurately. It learns what a red bicycle looks like from thousands of examples. Then, it applies that learning to new photos. This ability to learn and adapt is a cornerstone of what makes AI so powerful and so exciting for scientists and engineers. Let's zoom in on a clever part of AI, the neural network. Neural networks process information inspired by the human brain. Our brains have billions of neurons. Artificial neural networks mimic this structure mathematically. They help computers recognize patterns like faces in a crowd. Neural networks enable machines to learn from data. They power many AI applications like image recognition and language processing. Next, we'll explore how they learn patterns. All right, let's peek under the bonnet, shall we? What are these neural networks actually made of? A neural network has its own special kinds of building blocks. The most fundamental parts are called nodes, or sometimes neurons, just like their biological namesakes. These nodes are typically organized into layers. Think of it like a multi-story building. You have the ground floor, then the first floor, the second floor, and so on. Each floor represents a layer in our neural network. These layers work together to process information step by step, transforming it as it passes through. There are usually 3 main types of layers in a typical neural network. First, we have the input layer. This is where the information, our data, first enters the network. If you're trying to teach the network to recognize handwritten digits, the input layer would receive the image of the digit, perhaps as a collection of pixel values. It is the front door of our information processing factory. Each node in the input layer usually represents a specific feature or piece of the input data. For an image, each node might correspond to the brightness of a single pixel. So we have these layers filled with nodes, or neurons. But what does an individual artificial neuron actually do? Think of it like a tiny decision maker or a mini calculator within the network. Each neuron in a hidden layer or the output layer receives signals from many neurons in the layer before it. These incoming signals are like messages arriving at its doorstep. Each message or input has a certain strength or importance, which we will talk more about soon when we discuss weights. The neuron gathers all these incoming messages. It is a bit like a tiny committee member listening to various arguments before making up its own mind. Once a neuron has collected all its inputs, it performs a calculation. This is where the maths comes in, but don't worry, we will keep it simple. First, it usually calculates a weighted sum of its inputs. This means it multiplies each incoming signal by its corresponding weight, its importance, and then adds all these weighted signals together. Section 5. Connections that count understanding weights. We have mentioned that neurons are connected and that these connections have weights. Let's delve a little deeper into what these weights are all about, because they are super important. In fact, they are the key to how a neural network learns. Imagine our neural network is like a complex sound mixing desk at a concert. You have many microphones or inputs, and you want to produce a perfect sound mix, which is the output. Each knob on the mixing desk controls the volume or strength of the signal from a particular microphone. In a neural network, the weights are like those volume knobs. They determine the strength or importance of the connection between two neurons. Each connection between a neuron in one layer and a neuron in the next layer has an associated weight. This weight is just a number. If the weight is a large positive number, it means that the signal from the first neuron has a strong positive influence on the second neuron. It strongly excites it. Section 6. A little nudge. The role of biases. Now, alongside the weights that control the strength of connections, there is another important little helper in each neuron, except usually in the input layer. This helper is called a bias. Think of a bias as a sort of thumb on the scale, or a little nudge that helps the neuron decide whether to activate or not. While weights determine how much influence each incoming signal has, the bias provides an additional, constant input to the neuron that is independent of what the previous layer is sending. It gives the neuron a bit more flexibility in its decision-making process. Imagine a neuron is trying to decide if its weighted sum of inputs is high enough to make it fire. The activation function might say, you only fire if your total input is greater than, say, 5. Without a bias, the neuron's firing is solely dependent on the weighted inputs from the previous layer. But what if, for a particular task, we want the neuron to be generally more or less likely to fire, regardless of its specific inputs at that moment? That is where the bias comes in. A positive bias makes the neuron more likely to fire as it adds to the weighted sum. Section 7. Information on the move how data flows through. All right, we have our layers, our neurons, our weights, and our biases. Now let's see how information actually travels through this amazing structure. This process of data moving from the input layer through the hidden layers to the output layer is called forward propagation. Think of it like a message being passed along a chain of people. The first person, the input layer, gets the original message, the data. They then whisper it to the next person in line, the first hidden layer, who might slightly change it based on their understanding, and so on until it reaches the last person, the output layer, who announces the final version of the message. When you feed data into a neural network, say an image you want to classify, this data first activates the neurons in the input layer. Each input neuron might represent a pixel's brightness, for example. These input neurons then pass their values along the connections to the neurons in the first hidden layer. As we know, each of these connections has a weight. So each neuron in the first hidden layer receives multiple signals, each multiplied by its corresponding weight. It then sums up these weighted signals, adds its bias, and applies its activation function to produce its own output. This output is then passed to the next layer. Section 8. Learning and growing, how networks get smarter. So, the network can make a prediction using forward propagation. But what if its prediction is wrong, which it most likely will be when it is first created with random weights and biases? This is where the truly clever part comes in, the learning process. Neural networks learn through a process often called training. During training, we show the network lots of examples, and for each example, we also tell it what the correct answer should have been. For instance, we show it a picture of a cat, the input, and tell it, this is a cat. The correct output or label. The network takes the input, processes it through forward propagation, and produces its own output, its guess. Then, we compare the network's guess to the correct label. We calculate something called an error or a loss function. This loss function is a measure of how wrong the network was. If the network guessed cat and the answer was cat, the error is small. If it guessed dog when it was a cat, the error is large. The goal of training is to adjust the network's weights and biases in such a way that this error becomes as small as possible over many examples. It is like a student learning from their mistakes on a test. To make these adjustments, neural networks often use a brilliant algorithm called backpropagation, which is short for backward propagation of errors. Section 9. Why bother? The future is neural. We have journeyed through the world of artificial neural networks. Inspired by our brains, they power real-world applications, from smart email replies to social media recommendations to detecting diseases and enabling autonomous vehicles. They even create art and music. Understanding them is key to grasping future technology.